Welcome back to Data Science at Home, the podcast about machine learning and artificial intelligence. I'm Francesco, and today we are diving into something truly wild. I'm always very skeptical about topics like the one I'm going to introduce today, but this is actually very fascinating. It's about a neural network inspired by water vortices, which sounds quite weird, and it is because it's inspired by physics. And when things are inspired by physics, they definitely get my attention. We already had something similar on this show about pins or physics-informed neural networks, which was also a very fascinating topic. So we are talking about VortexNet today, which is a brand new architecture proposed by a researcher, Samin Wininger. Of course, I will provide the related links in the show notes of this episode at the official website, datascienceathome.com. Now, before you think this sounds too bizarre, because it does, let me tell you that this new network, in fact, might solve some of the biggest headaches in artificial intelligence right now. And so I'm going to explain what these problems are, what is the vision of VortexNet. I have to, tell you that reading the document it's not a paper, unfortunately. It's more something that they wrote on a blog post. In fact, it's quite hard. It's a hard math. It's very complex. So I'm trying to, simplify this idea, which I find it extremely interesting. So stick with us. So let me start from the problem with current artificial intelligence. So let's talk about what's broken now. Now, modern neural networks, the ones powering ChatGPT and many other large language models out there, together with image generators, recommendation systems, and so on, are definitely incredible pieces of software. But they have some serious limitations that we definitely know, and we know for a long time. That is, for example, the problem of vanishing gradients. Now, the problem of vanishing gradient is a problem that affects pretty much any deep learning network. And it's a problem that, how can I explain? Well, remember that game that we were used to play when we were kids? You have 10 friends. You tell something to the first friend, who tells the same thing or more or less that to the next one, to the next friend, and then he or she tells the same thing to even the next one, and so on until the last friend in the loop. Now, what happens is that if you have a certain number of friends, the last one usually gets an information that is quite distorted, or quite, the real information, the initial information is in fact kind of vanished or changed in whatever possible way. So that's exactly what happens with the vanishing gradients, to, of course, a better extent, which is more mathematical than just, telling stories to friends. So basically what happens with vanishing gradients is that the learning signal that travels backward through the network, in the so-called process called backpropagation, it gets weaker and weaker, right? Because why? Because you multiply these numbers by numbers less than 1 usually, or very small numbers. And so if you start multiplying a number by, for example, 0.5 a number of times, you are halving that at each single step until, of course, at the end of the, at the beginning of the network topology. So in the first layers, in fact, the early layers, they barely learn anything because the gradients are almost zero or very close to zero. And so this is the vanishing gradient problem. It's been a problem in AI since the very beginning, in fact. And so this can be one of those problems that might be solved with a new approach, the approach of VortexNet. Another very long time problem is the problem of long-range dependencies. So how can I explain this? Well, imagine you're reading a novel and something important happens in chapter 1 that only makes sense when you get to, let's say, chapter 20, right? Now, current AI systems struggle very much with these long-range connections. They can remember recent stuff pretty well, but connecting information across a huge gap, that's quite hard, okay? And it has been partially solved, I would say mitigated, with extending the context, but also using, attention mechanisms and all the other tricks that allow a network to, let's say, maintain these references, from the beginning to pretty much any point in the sentence, in the paragraph, or in the entire document, right? But the problem is not solved. The problem is there because you cannot extend contexts, indefinitely. Plus, extending the context will increase the computational resources that you need to solve that problem or to make that estimation or generation. So it's not, I would not call it a day if you just extend the context. Problem 3 is multi-scale information. This is something that we have spent a few words in a recent episode on this show. Think about how you understand a sentence. So you process individual letters and then words, then phrases, and then the whole sentence meaning all at once, right? Now, neural networks struggle to do this elegantly, the way we humans do it, right? They either focus too much on details or too much on the big picture. And they actually don't know how to make that switch. In fact, that our brain can do that very well. Now, researchers have created workarounds also about this. As I mentioned, transformers, the architecture behind GPT models and many others. They use something called attention mechanisms to help exactly with this problem, the problem of long-range dependencies. But there's a catch here as well. So they are quite expensive from a computational perspective. So that's what I said. These are problems that are solved kind of partially, so I would call it mitigated, not solved. The math gets really complex really fast, especially with transformers. That's why these things require an enormous amount of compute resources because the methods behind are indeed computationally expensive. So we've got these problems, weak learning signals in deep networks, trouble with long-range connections, and expensive computational tricks to work around these issues. And that's what VortexNet want to solve. Plus, I think there is a more philosophical, vision, in my opinion, which is: can we mimic, or by mimicking nature and physics, maybe we can get some improvements in the things we do today with GPT models. So the paper is extremely interesting, as I said at the beginning of this episode. The author looked at these problems and asked, what if we stopped thinking about neural networks as a series of, let's say, mathematical transformations, because that's what they are, and instead we started thinking about them like fluid dynamics. Now, this sounds weird, but stick with me, because that's exactly what the core of the episode will be about. Now, fluid dynamics is probably one of the most complicated phenomenon that you can study in physics. There are many things that are not yet solved. And also there is a lot of instability in the computation of this of fluid dynamics. So simulations can also be quite intensive in terms of compute time and computing resources. But I think that the mix of fluid dynamics and neural networks might be key and definitely interesting for solving some of many other problems, not just the three that I mentioned. So let me start with a phenomenon which is called the vortex street phenomenon, and I'm giving some relatively shallow information here just to make this episode relatively self-contained. But of course, I definitely recommend you go around and check these things on Wikipedia, even on ChatGPT or on large language models that you use, or even on Google. I mean, we should start using Google again, I think, but more on that in another episode. Search the information that you need, because of course this episode I will do my best to be self-contained as possible, but of course it's impossible to cover this complex information into one into one episode. So how can I explain vortex street phenomenon? Well, we all watched water flows around a pole in a stream, right? Or seen how air moves past a flag. You get these beautiful swirling patterns that we call vortices or whirlpools, essentially. They form, interact with each other. They transfer energy, because there is mechanical energy that is produced to actually move the flag, and create these very nice patterns, even with clouds, for example, when clouds hit a coast, and many other, things that happen in fluid dynamics. It's very interesting, and it's very fascinating when you actually visualize these things. Now, there is a phenomenon called a von Karman vortex street, where vortices alternate on either side of an obstacle, creating a wake pattern. Okay, you can see this in clouds flowing around islands from space. It's really cool. Now, here's the insight. These vortices are really good at transferring information and energy across different scales, right? Because a big vortex can spawn smaller ones, which in turn spawn even smaller ones, and so on. So you have this energy cascading, right? Energy cascades down. Information travels not just forward, like it happens for the neural networks that we know, but sideways, in loops, in spirals, in many other directions, and in many patterns, in fact, not just linearly. So what's the big idea? What if, instead of having information flow straight through a neural network layer by layer, we let it swirl? What if we created artificial vortices in the network, patterns of activation that rotate, couple with each other, and naturally transfer information across multiple scales? Okay? Now, this isn't just a metaphor. VortexNet actually implements the equations from fluid dynamics, specifically modified versions of the Navier-Stokes equations, which describe how fluids flow. So the beauty of this is that the author, I don't know if it's a precursor of this, or if there are other authors, other scientists who have tackled with this problem, but that's what I see, where I see the novelty. And the fascinating part is exactly like that, because Navier-Stokes equations, which are, by the way, extremely complex to solve, they describe how fluids work and how they flow, in fact. So transmitting this, transferring this knowledge to how neural networks might transfer information and, the learning patterns, it's something that I find extremely interesting. Now, let's break this down, and let's break it down. This actually works without getting lost in the math, because the math, as I said, it's quite complex. I personally found the paper fascinating and definitely a hard read, because I had to look at things from the past that I forgot, and it's not an easy read at all. Now, first, instead of regular numbers, VortexNet use complex numbers. Okay, numbers with both a magnitude and a phase. Okay, like a clock hand that can point in any direction and have any length. Right. This naturally captures rotation, which is perfect for vortex dynamics. Then we have the vortex layers. So each layer in VortexNet doesn't just transform information, but it creates counter-rotating activation fields. So imagine two whirlpools spinning in opposite directions. As information flows through, these vortices interact, they transfer energy, and they create patterns. Now, the math here is inspired, as I said, by the Navier-Stokes equations, which physicists use to predict how fluids behave. And there are three key components, which is the viscosity, the convection, and the forcing. Now, viscosity, this is like the thickness of the fluid, right? As the word says. It controls how quickly information diffuses through the layer. And this is a learnable parameter in VortexNet. So the network can figure out the right amount of viscosity for each layer. So if you think about air, water, and oil have different viscosity, to understand, what viscosity means for those who are not familiar with the terminology. So oil has a higher viscosity than water, for example, which is definitely higher than air. And so the way you transfer energy if you have a whirlpool in air, in water, or in oil, the speed and the way these whirlpools will react is completely different. It's indeed depending on the viscosity factor. Then we have convection, and this represents how the vortices carry the information along with them as they move. It's like how a river current carries a leaf, you know. And finally, we have the forcing, which is the input, right? The information coming into the layer, right? Now, there is another important number, which is the Strouhal neural number. I didn't even know this myself, so I had to search it out. So let me explain what vortex shedding actually is first, because it's it's central to understanding this architecture. So imagine you are standing in a stream, and you stick a pole vertically into the water, right? As water flows past this obstacle, something fascinating happens. Instead of flowing smoothly around it, the water creates alternating vortices, whirlpools that peel off first from one side, then the other, then the first side again, in kind of a regular rhythm. All right? If you have access to a river, you can try this yourself. I didn't, but I remember what happened when I was on holiday one time. Now, this rhythmic release of vortices is called vortex shedding, right? Now, it happens that with equations, you can predict these things, at least from a statistical perspective, because with the partial differential equations, when you change the initial conditions even slightly, things go extremely differently later on. Now, you can see this everywhere in nature. As I said, flags fluttering in the wind, power lines humming, even how blood flows past heart valves or veins. So the vortices don't just appear randomly, but they shed at a predictable frequency that, of course, depends on three things: how fast the fluid is flowing, how big the obstacle is, and, of course, the properties of the fluid itself. Now, in the 40s, engineers discovered they could predict exactly when vortex shedding would occur using a number, a dimensionless number, which is called indeed the Strouhal number. It's a simple ratio: the frequency of vortex shedding times the size of the obstacle divided by the flow velocity. And again, I'm oversimplifying here, but just to give you an idea of the quantities that are involved in this ratio. For most everyday situations, whether it's air past a cylinder or water past a bridge pier, this number tends to be around 0.2. Now, it's like a universal constant for vortex formation, right? Now, here's what the author of VortexNet did. He adapted this very concept into the Strouhal neural number for VortexNet. So in the neural network context, the frequency is how fast the activations oscillates in a layer. The obstacle size is the effective depth or dimension of the layer, and the flow velocity is represented by the activation amplitude. So the network uses this ratio to tune how oscillations propagate and how strongly different layers couple together. Just like in fluid dynamics, where the Strouhal number predicts when vortices will naturally form, the Strouhal neural number helps the network find the natural frequencies where different layers can resonate and exchange information efficiently. So think of it like this: if you have ever pushed someone on a swing, you know there is a natural rhythm, right? So you push at the right frequency and the swing goes higher with less effort, Then you push randomly and you might even slow it down, because it depends when you give the push. You are familiar with this concept. So the Strouhal neural number helps VortexNet find those natural rhythms for information flow. Isn't that fascinating? I don't know. I find it extremely fascinating. Now, here's where it gets even smarter, because, left unchecked, oscillations could either fizzle out or explode, right? There are many physical processes that explain this very concept. At some point, you don't need to push the swing very hard to make it loop eventually. You just needed to push in sync at the right time with a particular input force, right? Some kind of resonance. That's exactly, the adaptive damping mechanism that the author introduced with VortexNet. Because VortexNet now includes an adaptive damping mechanism. It's like an automatic shock absorber. It monitors the gradients, the learning signals, and adjusts the damping in real time. So when things get too chaotic, it adds more damping, and when things are too stable, it backs off. And this keeps the network at the edge of chaos, the sweet spot where systems are both stable and expressive at the same time. It's a tiny point, kind of an equilibrium, an unstable equilibrium, in fact, that allows you to have a network that is, stable enough but expressive at the same time. So we've got vortices, complex numbers, fluid dynamics equations in a neural network. This is pretty cool. Now, what does this actually buy us? Because we have to be more practical now. So, as I said at the beginning of this episode, solving the vanishing gradient problem, this is a thing that is actually very interesting to have. So remember the telephone game, or when we tell a story to a friend who tell the same story to the next friend, and so on until the last friend. So the message gets garbled in the first case. The problem of vanishing gradient is actually a real problem. VortexNet's resonant coupling creates alternative pathways for information. And so instead of signals having to travel step by step through every layer, they can resonate across the network, like how a tuning fork can make another one vibrate from across the room. And this means that gradients don't vanish as easily. The learning signal stays strong even in deep networks, because the mechanism to bring this information, this signal, is completely different. The other problem is the implicit attention without the cost, which is huge in my opinion, because in transformer models, attention mechanisms compare every word to every other word. So for 1,000 word text or tokens, whatever, that's 1,000,000 comparisons, right? So it scales quadratically. You double the length, you quadruple the computation. Now, VortexNet's vortex interactions create what the paper calls implicit attention. When two vortices come close, they definitely influence each other automatically through the physics of the system. So there's no explicit comparison, that is needed as we do now for tokens in transformers. And this could be much more efficient, especially for very long sequences. Then we have the multi-scale processing. Because vortices naturally create these cascades of different sizes, the network can process information at multiple scales simultaneously. So the big picture and fine details all at once, this is solved. Or well, might be solved. And that's exactly what we need for understanding complex patterns. And finally, we have dynamic memory. So instead of explicitly storing information like in a database, VortexNet's oscillating vortex fields create attractor states, stable patterns that emerge from the dynamics. Information gets encoded in the ongoing patterns of activity, like how a whirlpool maintains its structure even as new water flows through it. These are called stable attractors in dynamical systems, I remember from academia. So let's zoom out a bit, because this is becoming very complex, and believe me, it took me a couple of days to go through that paper and to summarize this in an episode. Now, what does VortexNet tell us about the future of artificial intelligence? Well, for sure, this is the typical example of physics-inspired computing, which is incredibly nice. So this isn't the first time, of course, that people have looked to physics for computational inspiration. There's a long history here, from analog computers that literally used water to compute, to recent neuromorphic chips that mimic brain architecture. We have actually made an episode about that. VortexNet is part of a growing movement to embed physical principles directly into neural network architectures. Of course, there is also physics-informed neural networks, or PINs. We also made an episode about that learn to obey physical laws, or neural ODEs, ordinary differential equations, that treat layers as continuous dynamical systems. And now this, networks that behave like fluids flow. Or, well, they try to. So, most neural networks are, how can I say, very digital in their thinking. Discrete steps, clear boundaries between layers. VortexNet is more analog, is more continuous. So information doesn't just hop from one layer to another, but it flows, it swirls, and resonates. And this might get us closer to, for example, how biological brains actually work. Because neurons, the real ones, don't just fire or not fire. There is no binary there. Right? They have complex oscillatory patterns. They synchronize, they form assemblies, and maybe vortex dynamics capture something fundamental about computation in complex systems. So, what could be some practical applications about this? Well, the paper suggests the typical ones, the one that we can definitely understand at this point of the episode, which is long sequence modeling. So tasks where you need to remember information over very long time scales, like analyzing entire books or very long medical records, or, I don't know, DNA sequences. Time series prediction is another one. Financial markets, weather forecasting, or any complex system with the patterns at multiple time scales, from the minute to the hours, to the days, to the weeks, to the years. Multimodal learning is a third application. So combining, for example, vision, sound, text in ways that naturally integrate different scales of information. Now, before we get too excited, we have to be realistic. As always, this show in particular, but this podcast in general, tries to stick feet on the ground and prevent any hype and not exaggerate with claims. So let's be realistic. VortexNet is still very theoretical, all right? So the paper presents the architecture and some initial analysis. Of course, there is also a GitHub repository where there are some very trivial example. I say trivial, they're not trivial. It's like MNIST predictions, the prediction of the digits from computer vision. Very simple benchmarks, okay? Nothing fancy, but it's interesting because the methodology behind it is completely different now. There are some of this initial analysis, but we don't have yet extensive empirical results comparing it to state-of-the-art systems. Okay. Now, there are many challenges here. Implementation challenges for sure. Implementing partial differential equation solvers efficiently is a non-trivial task. You need stable numerical methods that work with automatic differentiation. You need to carefully choose boundary conditions, initial conditions, time step sizes. This is hard, okay? Harder than just stacking standard layers, right? Then we have other challenges, computational questions, for example. So while the theory suggests this could be more efficient than attention mechanisms, we need real-world benchmarks, okay? And the question that we should probably asking is, does it actually save computation? How does it scale? What about memory requirements? And so on. So that deep analysis still needs to be done. The theoretical understanding, well, we need a deeper mathematical analysis. Under what conditions, for example, do these vortex interactions remain stable? How do you prove convergence during training? The connections to chaos theory and dynamical systems are, as I said, fascinating, but need to be formalized. And that's where the challenge comes. Now, the paper outlines an ambitious research agenda. Of course, open source implementation, which is always good, comprehensive benchmarks, hybrid architectures that combine VortexNet with existing approaches, and of course, deeper theoretical foundations. This is very early stage research, but it's pointing in a provocative direction. And that's what caught my attention, because today when I speak with friends and with colleagues, they ask me, hey, you do artificial intelligence, you do ChatGPT. No, ChatGPT is not artificial intelligence. There is much more than that. And VortexNet is just one tiny example of what else you can do rather than predicting the next token given a context of tokens. So VortexNet is where neural networks meet whirlpools. Not just that. It's a method that opens the doors to physics, which is always good because physics is sound, is proven, and most of the time understood by scientists. Now, whether or not this specific architecture becomes the next big thing, it represents something important: the willingness to fundamentally rethink how we structure artificial intelligence systems, not just tweaking hyperparameters, which is unfortunately what people and even good scientists have been doing in the last few years, or adding more layers to their already complicated topology, but asking, what if we borrowed principles from entirely different domains? Okay, maybe the future of artificial intelligence doesn't look like today's transformers scaled up. Maybe it looks more like a turbulent fluid with information swirling in beautiful complex patterns. That I don't know. I cannot tell. Time will tell. But yeah, this is definitely a very interesting topic and a very interesting paper to read if you can. And definitely look at the code, because also the code is quite interesting. That's it for today. Thank you so much for following this episode and following the podcast. And don't hesitate to drop by the Discord channel, or of course also the official website datascienceathome.com. Talk with you next time.